So now we're going to continue talking about relations, and we're going to talk about an equivalence relation. So the definition of an equivalence relation, we say a relation on a set A is an equivalence relation if R is all three of those properties: reflexive, symmetric, intransitive. So let's look at an example. Let's say our set A is the set 1, 2, 3, and 4. And then the relation here given by 2, 1, 2, 2, 3, 3, and 3, and 4, 4, 4, 4. This is an equivalence relation. So you should show that it's reflexive, symmetric, and transitive. We did that before, so I'm not going to do it again here. And so after we talked about we defined an equivalence relation, we also defined an equivalence class. And so for an equivalence relation on A and an element out of our set A, we defined the equivalence class, which is denoted by an A with bars around it, or brackets, is the set consisting of all elements in A related to this element A. So let's use our earlier example. Use our example back up here. So A was the set 1, 2, 3, 4. R was the set 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, and 4, 4. So if you write down the equivalence class of 1, 1 is related to itself and 2, and that's it. This is also the same as the equivalence class of 2. 2 is related to 1 and 2. The equivalence class of 3, the only element related to 3 is 3. The equivalence class of 4 is 4. So what this essentially does, these equivalence classes, is it partitions our set A into three sets. So if you notice, these three together, they form a partition of the set A. And remember, a partition, the union has to be equal to A, and the sets need to be pairwise disjoint. So now let's look at another relation, an equivalence relation. So let's look at another example here. Let's say R is the relation defined on Z by A relates to B if A plus B is even. We want to show that R is well, I'm just going to tell you that it's an equivalence relation, actually, but you should be able to show it. R is an equivalence relation. Find or determine the distinct equivalence classes. So let's start by picking an integer. So let's pick 0. And we want to figure out all the elements that are related to 0. So 0 is related to b if 0 plus b is even. Well, 0 plus b, that's really just b. So you need b to be even. So the equivalence class of 0 contains itself, and then 2, 4, 6, 8, and so forth. It's related to any even integer, so you can also have negative numbers, -2, -4. Now this isn't the only equivalence class because not all of the integers are contained in this set. So let's pick an integer that's not in this set. So for example, 1. 1 is in Z, but 1 is not in the equivalence class of 0. So let's find all the elements related to 1. 1 is related to b if 1 plus b is even. So what are the elements related to 1? Well, 1 is related to 1 because if I add 1 and 1 together, I get 2. 1 and 3. 1's related to 3 because 1 plus 3 is 4. 5. 5 plus 1 is 6, and so forth. So you can probably get the gist. -1 because 0 is even. -3. And now these two equivalence classes that I have here are contain all of my integers. The first one contains all the even numbers, and the second one contains all the odd numbers. So here I get two distinct equivalence classes, the equivalence class of 0 and the equivalence class of 1. So then we also talked about congruence modulo n. So for n greater than or equal to 2 and two integers a and b, remember that we defined a is congruent to b mod n if n divides a minus b. So for example, let's look at an example here. Let's say n is 2. Well then 4 is equivalent to 2 mod 2 because 2 divides 4 minus 2 because 2 divides 2. And so remember that congruence modulo n gives an equivalence relation on the set of integers. And from here we talked about the equivalence classes. So we looked, I think, previously, for example, at congruence modulo 4, and remember that our congruence classes correspond to the remainders we get when dividing by n.